This course module covers the technical fundamentals of wedge flow elements. Upon completion of this module, you'll be able to understand the basic principle of operation, recall the minimum Reynolds number required for wedge applications, identify the key components of the wedge primary element, recognize why remote seals are so important to wedge and its applications. The basic principle is this. If the medium to be measured flows through a pipeline whose cross-section is constricted by a primary device, the flow velocity at the restriction increases. The increase in flow energy causes a reduction in pressure energy. The pressure difference generated is accessed at two ports, one on either side of the restriction, and this differential pressure is used as the variable for the flow measurement. Downstream of the primary device, the increased flow energy is converted back to pressure energy. However, a part of the differential pressure is lost and is referred to as the permanent pressure loss. The proportion lost depends upon the type of restriction used and its relative diameter to the pipe. That means that it depends on the type of DP flow meter used and how much of a restriction to flow it produces. For a given DP flow meter technology, a smaller diameter restriction creates a larger DP, and a larger percentage of that DP is lost. A larger diameter restriction creates a smaller DP, and a smaller percentage of that DP is lost. DP flow meters rely on the fact that when a flow is contracted within a pipe, an increase in kinetic energy is seen with a decrease of potential energy, static pressure. The resulting pressure difference can be related to the velocity of the fluid, which is calculated using the square root relationship of DP flow measurement. By restricting the flow between two pressure taps using a V-shaped restriction, the wedge flow meter also adheres to this basic measurement principle. Wedge meters were originally developed by the Taylor Instrument Company, which later became part of ABB in the early 1960s for the measurement of slurry and other mining processes. It has evolved into a universal flow meter for gas, steam, and liquids. The wedge meter is particularly suited to the measurement of viscous and/or erosive fluids. The restriction is formed by a V-shaped obstruction, hence the name wedge, usually only on one side of the pipe, and it is characterized by the H/D ratio, which is the opening under the wedge divided by the internal meter diameter. The wedge meter is robust and resistant to wear, as it does not rely on keeping measuring edges sharp to maintain performance. It maintains its meter factor down to much lower Reynolds numbers than most other DP devices, down to Reynolds numbers as low as 500 in fact. The wedge element also allows the passage of solids in the fluid. The ability of the wedge to produce varying ranges of differential pressure is dependent upon the H/D ratio selected, where H is the height of the opening below the restriction and D is the overall internal diameter. So, for example, a H/D ratio of 0.4 means that 40% of the diameter of the pipe is open, with the opening being in the shape of a segment of a circle. As with an orifice plate, the size of the opening determines the amount of differential pressure produced for a given flow rate. Just as an orifice plate bore can be expressed as a beta ratio, so can the wedge, but the maths is different due to the difference in the opening shapes. In the case of wedges, if the equivalent beta ratio needs to be known, it can be calculated from the H/D ratio. Here we show approximate equivalent beta ratios for our standard H/D ratios. With this comparison, it's easy to see how the measurement technology of the wedge can be likened to orifice plate metering. This can often be an important concept to establish when dealing with a new wedge user who has a basic knowledge of differential pressure metering. The equations employed when using a wedge flow meter are a derivative of Bernoulli's energy equation. Factors such as Y, FA, and FPV are taken from engineering tables, whilst the balance are variables within the measured process. The wedge meter factor is Kd squared and is derived from the actual water calibration performed on a particular meter. After calibration, the as-built meter factor can be entered into the calculation, and the final dP at maximum flow can be calculated. It's important to have all the process variables available when performing sizing, and the user needs to ensure that they are correct. The wedge element has no moving parts. This means the wedge will have lower annual maintenance costs than devices such as the turbine meter or positive displacement meter. The V element has been designed without any sharp, wear-sensitive surfaces, which means the meter will not suffer any significant dimensional changes under normal wear, even with erosive solids in the fluid stream. This is a vast improvement over the orifice plate, because the accuracy of the wedge, unlike that of the orifice, is not dependent on the surface condition of the measuring surface or edge. Under correct conditions, the V element will last the life of the meter and will not need frequent cleaning or replacement. As the wedge restriction is symmetrical, bidirectional capability is available for interplant utility transfers, such as steam metering, or other applications where the process can flow in both directions. This can often remove the need for duplicate metering systems when two-way flow measurement is required. The dP generated is stable, meaning that low or draft range dP transmitters can be used with the wedge on any gas and steam applications that generate only low dPs. With several H/D ratios available in each meter size, the chances are that a line size meter can be applied to any application. This example serves to illustrate how flexible the combination of meter size and H/D ratio makes the wedge, with three sizes of meter being capable of comfortably handling a specific application. Let's summarize everything in a checklist before moving on to other topics. So, what have you learned so far? Wedges apply the basic dP flow meter theory of a restriction creating a proportional pressure difference. The restriction is V-shaped and gives long-term stability. A wedge meter can measure the flow in both directions.